This is a video for MD Youngblood and anyone interested in modeling. I'm going to basically show how I would build a model using the 4NEC2 software, building a model that MD Youngblood said he would like to model. Talk about why I do certain things, why I don't do certain things. Um, Basically just give the overall process of someone who's been doing this for several years. That's all. The first thing I did is I took a file called example1. I created a new folder where I'm storing this, copied it there, renamed the file. So this is the file that comes with this software called example1, just renamed. I'm using that as a base starting point. Um, that's basically the only reason. It doesn't like to necessarily start from nothing, although you can. Here we're going to open the file, and we're going to see basically two screens come up immediately. This screen up here in the upper right called main. We don't do much directly with the screen, but it opens up pretty much everything else that we do. And then this one at the bottom, what is my bottom left, this is the actual layout of the antenna being modeled. This will of course change because this isn't what we're going to be working with. We're going to come up over to the main window. We're going to look for the file called, actually before we do that, recommendation. Click on settings and go to auto segmentation. Here we have segments per half wavelength. I usually use 50. This will actually make certain things easier later. Usually when you're putting all the information in on what this wire is and its length, you have to put a segment count in. You want to keep those pretty consistent. Well, this will do a very good job of keeping all those consistent for us. So we don't need to worry too much about that. So again, under main, you go to settings, auto segmentation, type in 50, click OK. That'll get us a base starting point. That'll actually make things easier for us a little bit later so we don't have to do more math or more calculations than we have to. Then after that, we're going to go into edit NEC input file. It's this folder with a hand with the pencil in it, or it's a book, I guess it is. We're going to click on that. That's going to come up into this folder here, which is basically where we put all the changes to the dimensions of the antenna, where the source is, the frequency that we're using. If it doesn't look like this when you go into it, we're going to go back out to here. You go under settings and make sure NEC editor with the new in parentheses has the check next to it. If it doesn't, just click on it. That'll put you in this. This is the easiest to use and most advanced area, most advanced way to do this. There are other ways. There are 3 others listed in there. One of which is just a raw notepad window where you have to know how to type what and where, basically. So when we're in this window, the first place we're going to go is symbols. And then at the bottom, down here under scaling, there's meters, feet, inches, wavelength, custom, blah, blah, blah. I use inches, so I'm just going to change that to inches. Now, if you have a file that is all in meters, and you click inches, the system will try to auto-convert that for you. So you could do meters and then try to change it to inches. There are certain cases where that will not work, however. But if it's just everything is in meters and no what I'm going to call variables, which is what I'm going to show you next, or a little bit later, if it's just all the raw information in the geometry tab, which is where we started from, if you change this, it will change it. So you can go inches and go, oh, I want to know what it's like in meters. So you change it to meters, and it'll, or vice versa, and it'll automatically change it for you. From here, now we're going to come back to this tab because we're going to do things up in the main field here. That's an optional thing. It's how I do it. There are advantages which I will talk about when I do that, but it's not something you have to do at that point. Next, we're going to go over to frequency/ground. And the first thing we're going to do is change the frequency. We're not working with 300 megahertz. We're working with something much closer to 27.2 megahertz. Environment is in free space. We're going to change that to real ground. Down here, we'll see that that puts it on moderate ground. Moderate ground is very close to average. It's not right on it. It's actually more average than the average ground option. A friend of mine and I did some testing with it, and moderate was the most average. So that's what I tend to use, and I tend to ignore the average. Click on others. There's nothing really here. Comments. I'm just going to delete these. Dipole and free space. That's not what we're going to be playing with. So I just remove them. Now I'm going to come back to symbols, and I'm going to start actually thinking about the model in question. Like I said, this part is optional. This makes certain things easier later, and tools that I'm not going to get into, if you choose to eventually start using them, it allows for their use as well. And those tools are pretty powerful addition to this software. So it's a good habit to get into doing this sooner rather than later, which is why I'm showing this. We're going to essentially what we see is under symbols we have symbols and equations. So I'm going to just start with one. AH equals, see, 20 times 12 because the antenna was 20 feet high. A is 42. AH equals 42. Comments. Actually, 20 times 12 is that 420? No. My math is off today. 20 feet high, 240. I was way off. So basically we don't want this one yet. Actually, we'll come back to that. Basically what this is saying is anywhere in the geometry folder where I put AH, it's going to substitute it later for 240. The reason I'm doing this is if I want to change the height a little bit later, I just come in here and make one change and it can shift the whole antenna around. Things like that. The next thing is going to be, I'm going to do SL equals, I believe it was supposed to be 50 feet long, so 1, 2 times 50, 600. SL equals 600. SL is going to be side length. This is being used with a loop antenna. And I was told it was 50 feet long. I could be wrong on that. I'm pulling that from memory, but this is just a demonstration, so you can modify that as you see fit. I can come back and change that later if I want to see or do something a little different. Again, that's the advantage of using something like this. You don't have to. This is, like I said, completely optional. But maybe I'll get a chance to show how easy it is to make certain changes later with this. From here, we're going to go into geometry. This one is wrong, so I'm going to delete this one. This is the one that was already in here. It's the built-in. It was the already existing dipole. To delete a row, if you want to get rid of one, you click over here. You make sure it's all highlighted. If it looks like that, which sometimes it'll do, it's not highlighted. It won't work. But you click over here, you right-click and do cut rows, and it's gone. We're going to add a new row in, wire, tag 1. When it comes to tags, every wire you do has to have a different tag number. That's the only rule when it comes to tags. So 1, 2, 3, 1, 10, 20. I've done some where I'll have 1 through 10 at one group, and then 101 through 110 for another group. As I'm building it, it depends on the antenna. But everything has to have its own unique tag number. When it comes to segments, I just put 1 in. Remember before I went and showed you auto segmentation? If auto segmentation was set up, you don't have to worry about anything. You just put this in. There are a few things where you might want to put a segment count in. Certain ways of doing positioning a feed point will use them, but it's not something you have to do. And then I'm going to start working with the layout of the antenna that we're working with. We have X1, Y1, Z1. Those three basically go to a point on a three-dimensional space. Z is height, and we know the height in this case. We're making a loop, a horizontal loop, and we know that the antenna height will be at variable AH. Again, that's back here. AH equals 240, so the system will put 240 in where that AH is. This one is going to be the same. And then here it's just a matter of X and Y. Now what most people would do is just make four wires going around in a loop. I'm going to do something just a little bit different. This is again something then I will have to explain why a little bit later, and I will be happy to demonstrate this. I'm going to add in an additional fifth wire that I'm going to use where the feed point is. This is more or less, well, I'll have to show you later. I'm going to make it 2 inches by 0 inches and 0 by 2. And the radius. What's the radius for a 14 gauge wire? G2 inches. I'm going to make this out of 14 gauge wire. You'll want to use whatever it is you're going to use. There it is, 0.0641 inches. Copy that. Paste that in there. There's in this case, a 14 gauge wire. And then wire number 2, again, tag 2, everything has to have a different tag. We're going to go, basically what we're doing is continuing something. I'm continuing from this side. Whenever you continue, whatever's on X2, Y2, Z2, you start with the next wire, X1, Y1, Z1. So it's exact same as above. And then the other end of this will be 0 SL, side length. That's from back here in symbols. SL equals 600. So when I put SL here, it'll put 600 there. Height is still the same. Radius. And with this part, it's literally a matter of continuing this around. Here we have SL, SL. Okay, here are 5 wires. For whatever reason, it likes to hide the first one whenever you go into the second. It does this almost everywhere we go. I don't know why it is. It's just how the software has always worked. Now we're going to save this and close this. You may have to zoom in or out over here. Page up and page down zooms in and out for the most part. And here we have it. We have a loop. If I zoom right in on the feed point, turning it around here, we'll see that little individual segment that I made first. In this case, there's already the feed point there. That's fine. I'll show you that next anyway, but in case you need to modify that in the future, we're going to go back into the edit the NEC input file. Again, the book with the hand with the pen. It's going to go up. We're going to see all this information is already in because we put it in and saved it. When I saved it earlier, I used the save icon, which is these floppy disks. We're going to go under source. Now this is the one that was already there for us. I'm going to go ahead and delete this comment because really it doesn't have anything to do with what ours are. Here we have voltage source. You can change this to current source. I have done a lot of models and changed, and I've never seen voltage or current make a difference. There's also other options for more advanced things that really go beyond what anyone ever does. Here we're looking at tag. Remember in geometry, the geometry folder, everything had to have its own tag. Well, this is part Y. Use tag number 1. Under SEG, segment. This is normally what people would do with a lot of these, especially the older versions of this software. They would simply put they would have a total number of segments, and they would have to specify which segment they wanted on. So if they had, say, 9 segments, it would be the feed point. If they wanted it to be center fed, would be at segment number 5. In this case, we don't have to worry about that. We just type in 50%, and the system will figure it out for us. If you're if you're actually creating one of these, if you have to create one, say you're working with two antennas, or you deleted it and you need to make a new one based on what your antenna is doing, you'll want to put a 1 in for real and a 0 in for IMAG, which is short for imaginary. So real is 1, imaginary is 0. The system will automatically put a magnitude of 1 in. That's what you want to see. If magnitude is anything other than 1, something isn't in right. Now, on this screen, we're going to go ahead and do something else that I'm basically going to bring up, mainly because you want to use this for determining the feed point impedance, which will have to do with matching later. Now, this is something that a lot of people don't do when it comes to modeling, so when someone does something along these lines, it's that extra little step, you know? Again, if you're just showing a radiation pattern, in most antennas, it doesn't matter that much. But for our cases, because we want an accurate measure of the feed point impedance that we can then work with, you want to do this. Up towards the upper right corner, we're going to see the show source, which is checked. And next to that is a show loads. We want to put a check in there. That'll give us loads and some additional options. What we're going to do is load these wires up. The reason we're going to load these wires up is because the software itself shows these wires as being a perfect conductor. Well, metal, which is what these antennas are almost always made out of, is not a perfect conductor. Metal has a resistance to it. It's a very small resistance, but it does have a resistance. That resistance translates to a velocity factor. So if you don't do this, you will be much further away at the feed point than you should be when it comes to actually determining what that impedance is that you need to match to. We're not going to do wire number 1. Wire number 1 doesn't actually matter. I'll talk about that one a little bit later. But yeah, we just click on type, wire conductor. Tag, we're going to do a 2. First segment, 0%, just like the segments above. Last segment, 100%. So 0 to 100% of this will be whatever we set this to be. And we're going to change, I'm going to use copper, 14 gauge copper wire. If you're using a different conductor, go ahead and switch it. If it's a coated conductor, say copper coated steel, you use copper. These signals, when it travels up the antenna, never really makes it to the inside. It makes it to within microns, so small you won't even notice, of the surface. So it basically just rides the surface. So if you have a copper-coated steel wire, you want to use the coating, not the inside. I'm going to go ahead and do this for the other wires, and here again I show you one disappears. I'm just going to copy and paste. Oops. Something else that you can do here that I'm not going to get into too much, but in your case it might make a difference depending on what kind of wire you're using. Right now this is assuming bare copper wire. If you have a sheathing over it, be it PVC or another material, you click over here where we went to wire conductors earlier, and there's a wire coat option. Again, tag, first part, the last part, dielectric, constant, and radius. Now this used to have, I thought this had an option for basically which dielectric constant, there it is, they just called it different. This is what's on the outside of the wire, different materials, PVC hard, PVC soft, rubber. You need to know what the sheathing of the wire is made out of, Teflon. But you can go in here, use PVC soft, and the radius. Now this is the total. For the radius, you take the total diameter of it and just divide it by 2. But it's the total diameter of the wire with the covering on. You divide that by 2 and you put that in radius. I'm not going to get into that. If you're using that kind of wire, you'll have to put this in if you want accurate results. I don't normally recommend using this type of wire. I tend to use the wires made for antenna use. I know MFJ sells some, and a few other companies do. none of those have any of this type of coating. It's all those wires are just raw, usually solid copper or copper coated steel, depending on what the use is intended for. So I'm going to go ahead and remove this. But that's, if you're using that type of wire and you want accurate results, you need that to put that information in. We're going to save this. So here we went in, we looked at geometry. We didn't really look at it. We just basically came in and modified the source, and we put information in for what type of metals that was there. We save. Go back out here. Now, a point on this, we'll notice that in my case, and that is actually a square, even though it doesn't quite. It's the view looks at it at kind of an angle, no matter where we're at, so it doesn't show as a square. But that's a square. You'll note that it's not centered around the center point. That doesn't matter. We could have it centered around the center point. We can have one corner at the center point, like I have here. We can put it 1,000 miles on the x-axis. It doesn't really matter. The results for this particular test will be the same. The reason is what the system does is it actually looks out to what the pattern looks like at infinity. At infinity, it doesn't matter where around here you put the model. It's going to look this. You go far enough away, it's going to look the same. That's all that is. And so once we get all this information in, the next thing we're going to do is actually look at what it is we want to test. The first thing we're going to do is run a test on this to see how accurate the results are going to be. We're going to go up under the main window here, and we're going to click Calculate, and there's NEC Output Data. You can also just press, if the main window is selected, you can also just press F7. That'll bring us into this, which is where we want to be. We're going to start with the far field pattern. We're going to put a dot next to that. It's going to open up a section down here, and we're going to run average gain test. Now the results that we get with this aren't going to be anything resembling real world results. This is a test as a means of telling how accurate our results are going to be. And this is, when we run this is where we're going to get into that single segment feed point source that I showed you earlier. That's kind of a trick to get around potential inaccurate results. And that's going to be used up here. Something that I missed before, I'm going to cover it now and edit it in. The default for 4nec2 is not as smooth as what you normally see on my outputs. The resolution right here on the generate window is by default 5. If you get that, you'll get a bunch of lines that don't really line up smoothly. What you want to do to fix that and get the smooth results that I tend to get is change that to 1 and just leave it there. You only have to do that once. You don't have to come back. And now back to the main video. We're going to hit Generate. Wire losses in the ground. This always comes up when you run the average gain test. We're going to click OK. It shows that it's running, and it gives us a result. Now, we're not too worried about this result yet. What we're looking for is up here, AGT results. It's up in the main window. Where did I put my folder on that? According to the NEC2 information, an AGT of between 0.95 and 1.05 is likely to be accurate, which we are within that range. So we're within the range of what they would call accurate. Now, I tend to go a little more accurate than this. It's just my way of doing things. I like it to be right at 1. So we'll get to that here shortly. They have different ranges, which, as you move away, the model is usable for most purposes. Model may be useful but can be improved, or the model is questionable and should be refined. Basically, the closer you are to 1, the more accurate it is. That's what that's saying. I'm going to go in and make a change, and here we see what I'm going to do is go to the tag 1 wire, or wire number 1, tag 1, and change this, the radius. The reason this works on this, and when I have a single Basically, I made a single segment wire for the feed point. The reason this works is, while on the model it will actually show a wire going through the feed point, that wire is virtual. It doesn't actually exist. The feed point comes up with coax or its parallel feed line. One wire goes one way, one wire goes the other. There's not actually a connection through that. So any wire at that position is virtual. It doesn't physically exist. So I can go in and make changes to that, and it won't have any real effect on the rest of the stuff. So let's go. I'm going to go to 0.05. That's all this part is changing that, trying to get that to 1. Changing that 1 diameter. And if you're within the range, you don't have to do that. If you're going to be comparing multiple antennas together, it is something that I would recommend getting used to doing. You may have a quarter wavelength vertical and a 5/8 wavelength vertical. Within that range of is likely to be accurate, you can actually change the result for the better antenna to show worse and the worse antenna to show better. Although it's not a significant amount, you can actually skew the results. Which is why I go for, oh, 7. And when it comes to how much you change it, you get a feel for this over time. There we go, 1. Now I'm going to remove the average gain test and run the model. And we get a result that actually looks fairly similar to what it did before. This, by default, goes to the direction that shows the most gain. As we can see, it's not the same on both sides. We can actually take a look at a different view. This is looking at it from one of the sides. The side that would show the most gain in one of the directions. We can also look at this from top down. We click on, under the pattern box, the vertical plane, or you can just hit spacebar. That's what it looks like showing from top down. So we have, when we set this up, 45-degree angle maximum radiation in 2 directions. We're getting 12.7 dBi of gain. That's decibels over isotropic. But that's the pattern that we're looking at. Now, if we look above, we have impedance. We have, if you're used to X and R, or R and X, next to impedance, the 1655, that is R. And then you'll see a minus J and a number. That's the number minus or plus in X. So we have an R of 1,655 and an X of negative 731. Now that's something that we can do some things with later, which I might show in another video. As we scroll down, we can see that this antenna has an SWR at the feed point for a 50 ohm feed line of 39.6. Continuing down, there's an efficiency and a radiation.EFF. Basically what the efficiency is this is losses in the structure itself. So instead of using a perfect conductor, we changed a bunch of the wires to copper. Well, because of the copper, we actually have a structural loss of 1.179 watts. This is assuming a 100 watts input, so 1.1, it's actually 1.179%, which goes to radiated power, which is the same as the efficiency. This and this when it's 100 watts, the radiated power when it's 100 watts, and the efficiency when it's 100 watts will always be the same. What radiation efficiency is it takes into other factors, like the earth below the antenna. It starts with the efficiency that you started from, and then any other losses like ground losses or what have you are factored here. Right now with this antenna of the 100 watts coming in, 65.79 watts will make it to the far field. Will actually be productive out for other people to pick up. That's what radiation efficiency is telling us. Just one more little thing that you might watch over time. It'll give you some information once you get used to seeing it. Is RDF. What RDF? I forget the what it translates to, but that's saying how directional it is. The more directional an antenna is, the higher this number. So an omnidirectional antenna will have a lower number than, say, a Yagi pointing in a single direction. Omnidirectional antennas tend to be between 5 and 8, 5 and 9. As we can see, we're a little more directional than an omnidirectional antenna. That's basically what the information in here is telling us. There's a few other things you may look through, but nothing that we have to worry about so much. That's basically making the antenna. Okay, continuing on. The rest of this video really doesn't have anything to do with modeling. It's a means of matching. I can actually use this particular software that's on the screen right now to actually show what I can and can't get with the feed line. It's based on the Smith chart. It is actually two different types of Smith charts interposed on top of each other, and basically it's just used to show what we can and can't do with matching. The red dot here, actually let's go over. I have the load impedance. This is what the antenna has. I have the source impedance. That's what we're basically matching to. And down here with the Smith chart 0 ohms, this is the impedance of the feed line itself. We're using 450 ohm window line as per MD Youngblood's instruction what he wanted to use. The load impedance right here, the real and the imaginary, comes from right next to impedance. The source impedance, I started with 50 and I couldn't get it there, so I made some changes. I basically slowly changed it until I got to where I could match it or get real close to that match. Switching over here to the Smith chart, the red dot, that's your load impedance. That's the impedance that you're getting with the antenna. This green circle is everything that you can get with the 450 ohm window line. That represents every impedance. I can go up here and I can read impedance. I can go over here, I can read impedance. Basically, like I said, every impedance is represented on this line. Now, from this line that goes straight across this chart, it's the only straight line on this chart. That's everything on that line is resonance, or x equals 0. So where this line crosses here, that's x equals 0. And where this line crosses here by where the blue dot is, that's x equals 0. The blue dot is actually what we're going to with this particular setup. This will have a very high impedance. It will be higher than the 1655 impedance that we currently have, the real part of it. But it's actually higher than what we have down here. This one is much more reasonable for us to work to, so this is why I'm heading towards this point. But to go from here to here, that's a quarter wavelength transformer that you see. The 75 ohm coax will go from 50 ohms to a little over 100 ohms. That's a good representation. That's a good explanation of what's happening here. So you have one side of it here and one side of it here. In this case, our load isn't on this line. Our load is actually a little below the line, well, that's where our load is. So what we want to do with this is start from here and figure out what it is to get to here. And that won't get us straight to 50 ohms, but it will get us to 100 ohms, which you can, as I was talking about earlier, and as I know MD Youngblood knows, you can then use a 75 ohm quarter wavelength feed line as a transformer for that to get to this point. So this is well within, as far as I'm concerned, something that he's capable of dealing with, or at least in theory. So what we're dealing with is a little less than a quarter wavelength. We're actually 12 degrees less. So 90, 80, 78 degrees to go from here to here instead of the 90 degrees. What I would actually do in this case, based on experience working with this type of feed line, is when I'm attaching the feed line, the window line, I wouldn't necessarily solder it in place. I'd wind it tightly where it needs to go, and then I'd start it at the quarter wavelength, and I'd shorten it little by little until it gets us to the best SWR. That's how I would do it. It's not like coax where you have to continually put on new connectors every time. You can cut it off, wind it, cut it off, wind it, and when you get it where you want it, you can either permanently crimp it or solder it at that point. It's in that way much easier to work with that type of feedback. But for this, I would start with the 90 degrees, the quarter wavelength, and I would just shorten it little by little until I get where I need to be. And like I said, this won't go straight down to 50 ohms. It will let us get pretty close. It will let us get to 100 ohms, which is something that should be working. Well, that's that. If you have any questions, MD Youngblood, or anyone else on the forum, feel free to ask. I'll also answer questions in YouTube. That's that.